Okay.
I think there's a little delay from,
Okay.
but
So
now,
yes. Is
now
it
we can,
okay?
yeah, that's okay. That's okay. We can
Okay.
see it. Maybe you can shift to the presentation mode so that we can see it full screen.
Okay.
That's wonderful. We can see it very well.
Okay. So my topic is going to be about the Nernst equation in equilibrium electrochemistry. I will deal with the content of chemistry and the didactic methodology. These two combined make what is known as pedagogical content knowledge. I mentioned earlier my connection to Italian chemical education, but I have further connections. It was the magazine La Chimica nella Scuola, where I published my first article in English. That was about the hierarchical organization of descriptive chemistry back in 1994. Rinaldo Cervellati had called me to contribute. And later in 1998, with Liberato Cardellini, we shared an article on problem solving, which was written in Italian with an abstract in English. And talking about problem solving, I take the opportunity to advertise a recent book I edited. That's Problems and Problem Solving in Chemistry Education, published by the Royal Society of Chemistry in 2021 in the
Excuse me.
Advances in Chemistry. Yes?
Excuse me, Georgios. Are you scrolling the slides? Because we still see the first one. So I don't know if you're...
Scrolling.
Are you moving on your presentation slide after slide? Because we still see the first one.
Let's check what can we do. Do you see now a change of slides?
Actually, we don't. Maybe you can remove stop sharing and then share again and see how it works. That's curious because
You still don't see.
now we see it move. Yeah, now it works. Now
Okay.
it's fine. We are
So
seeing Chimica nella scuola.
Okay, I will run through the slides I spoke about earlier. The article in the Chimica nella Scuola.
Thank you.
The article with Liberato Cardellini on problem solving.
Yeah.
And the book of the Royal Society of Chemistry on problems and problem solving in chemistry education. It's okay now?
Yeah, it's perfect now.
Okay.
Thank you.
Well, we all know that electrochemistry is an important branch of science and technology, also a traditional part of physical chemistry. It is being included in the curricula of high school. Also, it's taught within the general chemistry and analytical chemistry courses. In secondary education, various topics are covered like electrolytes, ions, electrolytic conduction, oxidation reduction reactions, and electrochemical cells. I take the chance also to let you know of a book for teachers edited by Keith Tabor and published by the Association for Science Education in England. The title of the book is Teaching Secondary Chemistry, and I have contributed a chapter to that entitled Electrolysis, Electrolytes, and galvanic cells. Earlier, we heard a lot about the contribution of electrochemistry to energy transfer. We know that electricity is the most useful and widespread form of energy transfer, mainly produced by power generators using combustion materials. But this way of energy production has two major drawbacks. One, the low thermodynamics dictate that the efficiency of thermal engines is well below 100%, can be as low as 40%, and combustion reactions produce gaseous products that pollute the atmosphere and the environment. On the other hand, electrochemical energy conversion is based on the direct transfer of electrical energy with a very high efficiency during a spontaneous chemical reaction that occurs in an electrochemical cell. An example is the cool combustion of hydrogen producing just water. Now, electrochemistry is divided into two major branches: ionic electrochemistry and electrode electrochemistry. Electrode electrochemistry studies electrochemical cells, which are being divided into galvanic cells and electrolytic cells. Batteries are electrochemical cells, and according to Akira Yoshino, who is considered as the father of the lithium-ion batteries, battery technologies are electrochemistry, a complex and difficult interdisciplinary field. This brings us to teaching and learning, and we see that electrochemistry is a complex field, and it is here that education studies have to contribute. We heard earlier about other alternative to lithium-ion batteries. Sodium comes to the battery world. This is a recent article in Chemical and Engineering News. But there is a question there. Taking into account that sodium-ion technology is ready, cheap and safe, the question is, can it oust lithium-ion? Now, another division is between equilibrium electrochemistry and dynamic electrochemistry or electrochemistry kinetics. In this presentation, the emphasis will be on equilibrium electrochemistry, especially on problem solving involving the Nernst equation. It's based on an article I published recently in a special issue of the Israel Journal of Chemistry. It was a review of teaching and learning electrochemistry. That paper reviews relevant studies and considers strategies and approaches for the effective teaching of electrochemistry. The study of the literature has revealed many conceptual difficulties and misconceptions, which have been reported in the educational literature. Topics such as electrolytes, redox equations, and electrochemical cells cause many difficulties. Other studies have considered teaching for overcoming misconceptions. Usually at the general chemistry level, but also at the secondary level. Fewer studies have taken place within university physical chemistry courses. And I'm saying this because I have been teaching electrochemistry for about 30 years in my department. So this presentation focuses on pedagogical content aspects of problem solving in equilibrium electrochemistry, especially problems involving the Nernst equation. I will describe shortly 3 studies with Greek University chemistry students. 2 are in their master degree program, and these deal 1 with algorithmic problem solving ability, 2 with practice on problem solving, and 3 with the effect of the format of a problem, that is, if it is a composite problem or if it is a step-by-step problem. Pedagogical content knowledge is a combination of pedagogical knowledge and subject matter knowledge. So it brings together pedagogical aspects which are related to subject matter content. To provide you an example of what one can consider as pedagogical, I show you here a combination of a galvanic cell with an electrolytic cell. The galvanic cell produces electricity. An oxidation reaction, half reaction occurs at one electrode. Electrons are released one circuit. So this is the anode, and come down here to the one electrode of the electrolytic cell. So here where electrons go up, it's the anode, and here it's the cathode. This electrode where oxidation takes place and the electrons are released is the negative electrode, and we label also this electrode in the electrolytic cell also as negative electrode. Now this is the cathode. Reduction takes place at the cathode, oxidation at the anode. The current, goes through the electrolyte. There, electrolysis, the phenomenon of electrolysis occurs. Electrons released go up here and go down here. So we have the anode of the electrolytic cell and the cathode. So one important thing is that both in the galvanic cell and the electrolytic cell, oxidation occurs at the anode and reduction at the cathode. The difference is that anode is negative in the galvanic cell, but positive in the electrolytic cell, and the cathode is positive in the galvanic cell, but negative in the electrolytic cell. So this trick can make plausible the differences, the commonalities between an electrolytic and a galvanic cell. Let's go on. For the 3 studies I'm going to describe, I use data from final semester examinations of the Physical Chemistry 2 compulsory course taught to second year, 4th semester chemistry students. The instructional method was basically didactic, that is traditional lecture, but the instructor, which was myself, used his knowledge of student-centered, active learning instruction and often employed student questioning and direct involvement in the construction of new knowledge. For this course, I distribute to the students Greek notes I wrote based on the very important book, Modern Electrochemistry by Bocchus Reddy, first edition, which I read and used, published in 1970 in 2 volumes, volume 1 ionics, volume 2 electronics. And then came the second volume in 1998, 3 volumes now. Volume 1 is about ionics, as in the first edition. Now, The second volume of the first edition is divided into two now. Second volume is Fundamentals of Electronics, while the third deals with applications, electronics in chemistry, engineering, biology, and environmental science. Here is the cover of the notes I distributed to students. First edition 1986, last edition 2014. The course included ionic and electrode electrochemistry. Ionic electrochemistry involved the study of ion-solvent interactions, ion interactions. This includes the famous Debye-Haeckel model. On the other hand, electrode electrochemistry contained both equilibrium and dynamic electrochemistry. As is apparent, great emphasis was placed on dealing with equilibrium electrochemistry, especially with problems involving the application of the Nernst equation. Now, study 1 is about students' performance and conceptual difficulties when dealing with algorithmic problems in equilibrium electrochemistry. Here, I give you an example of a problem. We are given this galvanic cell at a temperature of 298 degrees Kelvin. And the questions are, question 1, write the spontaneous reaction that takes place in the cell. Also calculate the standard cell potential difference for the cell. And question 2, calculate the chemical equilibrium constant for the overall cell reaction at 298 Kelvin. The data given are the two half reactions, two redox couples, and the values of the standard potential. Here is a table with data of the findings. I have here two sets of data. One is A, the other is B. And on the third column, I have the percentage of success rates in this corresponding subproblem. And the final column is the percentage success rate in the overall electrochemistry exam. The success rate in the overall exam is considerably higher because it included also questions which are simply recall questions. So the problem part was more demanding and had lower performances. I note here a very low performance in 1A question, 6.3%. And also in the 4A and 4B parts, we have low performances, 27%, 22%, and this was here included what is a composite problem, and we're going to talk about it later. The very low success rate, 6% in the first question, can be attributed to the difficulty of this redox couple, which belongs to what we call an electrode of the second kind. Many students here used one of the following half reactions instead, where the second reaction is irrelevant, involving the 2+ mercury ion. The first one is okay with the ion, but it uses the ion and not the insoluble electrolyte. Electrodes of the first and the second kind are important to distinguish. In the case of the first kind, the electrode contains a metal plate or a wire which is immersed in the same metal solution. So here we have silver solid metal immersed in a solution of a soluble silver cation salt. An electrode of the second kind contains a metal plate or a wire which is coated with the insoluble salt of the same metal. Here we have the sodium chloride electrode. Students find the second kind of electrode very, very complicated. They usually are sticking to the electrode of the first kind. That is, they consider that using the silver cation is equivalent to using the insoluble salt, silver chloride. So here was the electrode of the first and the second kind, which caused the difficulty. Here is again the table with the results. Now, some conclusions about the study. I call these critical details, which are important for teaching and learning. Difficulties were encountered in completing the more complex half reactions, predicting the spontaneous reactions, and calculating the standard potential value. Several students did not take account of equilibrium, the following equation: delta E equals 0. Also, significant confusion was noted between the application of the European Convention and the application of the American Convention for the sign of the standard electrode potential. If we consider the European Convention, we have an invariant sign for the electrode potential. Here I write the half reaction size reductions. This is a common practice, a recommended practice. And here the values and signs of the potentials coincide with the so-called standard electrode potentials according to the European Convention. If I want to calculate here the potential, the standard potential of the cell, I have to subtract the smaller value from the larger value. So here I arrive at a value of plus 1.99, and this is a positive sign which shows a spontaneous reaction. And the overall reaction is here. Now, if I reverse the reaction and I write it as an oxidation, if I stick to the European Convention with the invariant sign, I have again to have minus 0.762. This is for people, for students to grasp. Taking the American Convention is more common. One reverses the half reactions, writing them as oxidations this time, and also reverses the signs of the potentials. Now, if we want to find the spontaneous reactions, we have to combine equation 3 with equation 2, and to calculate the standard potential of the cell, we have to do the same with the standard potentials, half potentials, to add E3 with E2 to arrive at the same plus 1.099 volt value. So structural propositions which are deriving from this study is that we must pay attention to the relevant concepts and the relevant conceptual details. It's preferable to stick strictly and consistently to the use of the European Convention. Small group tutorials up to 15 students in each group can be useful The teaching will be carried out using modern methodologies such as active learning, teacher-student interaction, and collaborative learning. Emphasis should be placed on encouraging and insisting that students carry out numerical calculations. In the present situation, a significant proportion of students did not deal with numerical calculations at all, and from those who did, very few got the right result. Students really are scared of numbers and of numerical calculations. Now I move to the second study, a study on Greek students' lecture attendance, in-course practice on problem solving, and success in final examinations in equilibrium electrochemistry. The interactive compensatory model of learning proposed by Crippen and Brooks was employed here. This places importance on motivation, practice, and feedback in instruction. It is assumed that three entities facilitate learning: prior knowledge, ability, and motivation. According to Crippen and Brooks, at the core of quality instruction is a model of learning that considers the vital role that motivation plays for building well-integrated cognitive structures. Also, instruction that requires students to learn from and interact with structured worked examples of closed-ended problems is consistent with contemporary models of human learning and produces efficient and effective results. The research questions for this study were: one, to find if provided students individualized help and feedback with electrochemistry problems during the course contributed to better achievement in the final exam. And the second question, to examine the effect of student attendance of the course and their engagement with the exercises on their achievement. The findings: participation in the exercises was varied, with 51% of the students participated in only one exercise. A large majority, 91% of students who participated in the exercises, independent of the number of exercises, took the examination, the written examination. 3 of the students who had participated in the exercises, about 2/3, 65%, succeeded in the exam. And 4, over half of the students, 55%, with high participation in the exercises, 3 or more exercises, were successful in the final examination, while in the case of the low participated students, the pass figure was lower. The overall performances of the students in the exams was low, reflecting a poor knowledge of electrochemistry. The conclusion was that there is a need for an overall change of the organization and operation of teaching in Greek universities. Students' attendance at the lessons must be regular, if not compulsory. Projects and exercises should be assigned by all instructors, followed by constructive feedback to the students. As you understand, I'm saying this because these things is not a practice in Greek universities. And as a result, we have many problems with many students don't attending the lectures, don't taking the exams, and failing the exams many times when they take it. Note that they can sit the exams as many times as they wish. The introduction of tutorials and exploitation of the internet could certainly contribute to motivating and engaging students. This is important and can contribute to better engagement of the students. Now, my final study 3, the importance of the formatting of the problem, dealing with student performance in the composite and the step-by-step electrochemistry problem. This is an example of a composite problem. A chemist in Mexico City, where the atmospheric pressure is 71 times 10 to the 4th Pascal, that is 0.7781 bar, determine the pH of a solution at 25 degrees centigrade by making it a solution in a hydrogen electrode and measuring the potential of the electrode relative to some reference electrode, a Kalman electrode, which, by the way, is an electrode of the second kind. In calculating the pH of the solution from the potential measurement, the student assumed erroneously that the hydrogen gas bubbling out of the hydrogen electrode was at a pressure of 1 bar. If he found the pH to be 5.00, what was the correct value? This problem and many similar problems were taken from the book Problems in Physical Chemistry, an old book which has a quite good collection of this kind of demanding physical chemistry problems. The step-by-step problem has the problem split in sub-questions. In this particular case, we have 4 sub-questions. Sub-question 1, write down both the half reaction that takes place at the electrode involved in this problem and the Nernst equation for this half reaction. Sub-question 2, identify the gas that was bubbling out of the hydrogen electrode. Sub-question 3, calculate the potential of the above half cell at 25 degrees. And sub-question 4, calculate the correct. This is the table with the. We have 3 sets of data. One is from the exam of June 2005. Here we have a mean performance of 38. Is it okay with my presentation?
Yeah, the presentation is okay. From time to time, we don't hear you very well. Probably there are some problems on the line, on the internet line, but
Also,
we are following your talk.
I will move the microphone closer to my mouth.
Okay, no, that's fine. But I don't think it's a problem of the microphone. I'd rather think it's a problem of the line. But anyway, we are managing to follow you. Thank you.
Okay, thank you. We are about to go to find the end. And let's hope that's going to be the end of the problems as well. So here in the composite problem, we have 38% mean performance in this exam, while in the stepwise problem, the performance was 61%, much higher. These 2 sets of data are from the same exam, but one is with students with practice in problem solving, the other with students without practice. So we have here 37% in the first case versus 27% in the second case. And the stepwise problem has much higher performances here, 56 compared to 37, 46 compared to 27. Also, we note that students with practice had higher performance, 37 versus 27, 56 versus 46. So let me run to the overall conclusions and recommendations. The procedure involved in solving a demanding equilibrium electrochemistry problem requiring the application of the Nernst equation to a galvanic cell is complex and accounts for students' difficulties when dealing with such problems. Although the nature of the solutions is such that the problems can be turned into algorithmic exercises through extensive practice, the fact that most students find these problems hard and commit numerous errors can be explained by their lack of conceptual understanding. Critical details here: even students with acceptable performance in the examination had difficulties dealing with topics such as writing the two-half reactions and the overall cell reaction, the equilibrium condition in a galvanic cell, where the potential difference value, the standard value, the potential difference value is 0, the differentiation between electrodes of the first and the second kind, and the replacement of numerical values in the Nernst equation in the calculation of the final numerical result. So both instructors and students should bear in mind that it is the two-half reactions that actually take place in an electrochemical, galvanic, or electrolytic cell, with the overall cell reaction being the logistic result of combining the two-half reactions. The overall reaction is usually a redox reaction, but it need not be so. It can also be a reaction which shows the dissociation of an insoluble salt into its two ions, which is combined with the calculation of the solubility product contact constant. Other recommendations: students should be given good practice in writing redox half reactions, both in acid and basic solutions. Decided between the two half reactions in a galvanic cell, which will occur as the oxidation and which as the reduction on the basis of the relative standard electrode values. It is the one with the higher algebraically value which will occur as a reduction, while the one with the lower algebraic value will occur as an oxidation. Finally, consistency in using the European sign convention should be secured. An important thing is that the solvent, water in most cases, being involved in the half reactions, should also be considered, could also take place in the reactions. So in a node which is negative in a galvanic and positive in an electrolytic cell, we have oxidation of water to oxygen in acid solutions and oxidation of hydroxide ions to oxygen in basic solutions. These two half reactions are not the same, and this is also shown by the having different standard potential values. In the cathode, which is plus in a galvanic and minus in an electrolytic cell, we have hydrogen ion being reduced to hydrogen gas in acid solutions, and water being reduced to hydrogen gas and hydroxide ions in basic solutions. Again, these are different reactions, half reactions, and have different standard potential values. It is important to realize that the three studies reported were carried out within the specific context of the Greek higher educational system, with its distinctive features such as traditional didactic methods of teaching, lack of compulsory attendance at lectures by the students, and in principle an unlimited ability to sit examinations. There are, of course, many approaches that can be used to motivate students to engage more actively with their courses rather than merely passively attending the lectures. It has been restored in the literature. That's 2005. It's about physics tutorials, published in the International Journal of Science Education. The introduction of student-centered voluntary workshop tutorials in a large first-year physics course based on informal cooperative groupings with structured worksheets and shorthands on activities resulted in about 80% of the students attending more than 2/3 of the tutorials. By discounting the students who had attended very few tutorials, it was found on average that exam marks improved significantly with increased tutorial attendance. Also, students' attendance at lectures should be regular, if not compulsory. Projects and exercises should be assigned by all instructors, and this should be followed by constructive feedback to the students. The introduction of tutorials, exploitation of the internet, and the promotion of collaborative learning are all likely to contribute to motivating and engaging students. So, to end, one can have a systematic approach to problem solving. Critical details should be borne in mind. A number of steps in the approach to problem solving should be taken into account. These are as follows. 1, what is the target question? 2, what do I need to know in order to answer the target question? 3, am I able to solve the problem? Or if there is a new unknown, I should go back to step 2. 5, do I have all required data? If not, what are the data do I need and where can I find them? 6, if yes, replace the data in the final equation and perform calculations to arrive at the target result. And 7, check against data or general relevant knowledge if the result is reasonable. I think I have to stop here. Thank you very much for your attendance. I have examples here where I applied these conditions, but I think my time has run out.
Well, actually, you have still a few minutes if you wish to add some comments or just
Yes,
go ahead.
it was just an application of my previous number of steps one should take to solve the problem. I have an example here of a non-spontaneous reaction, which is this reaction here is the dissociation of silver chloride into its 2 ions. This reaction can be used for calculating the solubility product constant. Again, we have to consider the 2 half reactions. One is a reaction of the first kind, and the second is a reaction of the second kind. The first has a larger standard electrode potential value than the second. So the first, in the spontaneous case, will occur as reduction and the second as oxidation. And the overall reaction, which can be found by subtracting half reaction 2 from half reaction 1, is the precipitation of dissoluble silver chloride by reacting 2 solutions, one with a soluble silver cation salt, the other with a soluble chloride salt. In this case, the standard potential difference is found by subtracting the smaller from the larger values. It's 0.58, it's positive, the reaction is spontaneous. The opposite reaction, I have to take for this a negative sign for the standard potential difference, minus 58. So this marks the non-spontaneous reactions. This is a critical point students should be paid attention to. And here are the calculations which lead to the calculation of the solubility constant, a value which is much lower than 1. I have to acknowledge the contribution of the 3 students who did their master's degrees under my supervision in the 3 studies I described: Mrs. Vasiliki Exarchou, Mrs. Konstantina Malamu, and Mr. Elias Megalonidis. I have also to thank again the Division of Chemical Education of the Italian Chemical Society and Dr. Elena Maria Gibaudi for all the collaboration we had for many months now for preparing this contribution of mine. So I have to say grazie. Thank you. Σας ευχαριστώ.